In this lesson, let's see how orthogonal subspaces to any given vector subspaces are obtained, and also how to obtain their complementary subspaces. We are going to build these subspaces based on the orthogonalization algorithm. You must remember that the orthogonalization algorithm has been designed just for this function. Given a vector, what the algorithm does, is to get the corresponding orthogonal subspace, and its complementary subspace. Later, we will apply it to more complex cases and other applications of algebra. We use an example, to show clearly how it works, and the properties that the algorithm has. We start, first, in the iteration 1, introducing a vector in the first column, the vector a1, which is in a fuchsia color, and what we do is we pivot. We calculate the scalar products, we pivot, and we get the matrix that appears in iteration 2. Let's see what is happening. What happens is that if we multiply that vector a1, by the transformed pivot column, which is the vector in yellow, the fuchsia vector by the yellow vector, gives us a scalar product with value 1, and if we multiply the vector that I have entered, the a1 in fuchsia, by the blue color, by the three blue vectors, we get scalar products 0, which means that the vectors in blue are perpendicular to the vector in fuchsia color a1, and that the yellow vector belongs to the complementary set. Because the scalar product is not 0, but it is more, it gives a scalar product with value 1. This means that the orthogonal subspace to the subspace generated by the vector a1, in fuchsia, is a space generated by the three vectors, that have the v in iteration 2, those that are blue, and that the complementary subspace is the subspace generated by the vector w, which is in yellow color. But surprisingly, and the truth is that it seems like a magic game, because it's incredible. If we enter other vectors, as vector a2, and pivot, and then a3, in iteration 3, and pivot, or a4, in iteration 4, and we pivot to the end, this property they had these vectors, in yellow and blue, has been preserved. What is the meaning of this? It means that the fuchsia vector a1, by the blue ones, provides 0 scalar products, and the scalar product of that vector by the yellows, it's still 1, that is, this property, which we had in iteration 2, that a1 by a vector in yellow gives the value 1, and for the others, gives 0, is preserved throughout the following transformations, that is, the transformations do not alter this property. Let's go to the case of the second vector a2, which we enter in the table. If in the iteration 2, we enter the vector a2, the 0 1 0 1, and pivot, we get another matrix, and if we enter the vector a3, and we pivot again, we get another matrix in iteration 4, and if we enter a4 in iteration 4, we get another matrix, which gives us the final table. Well, that fuchsia vector a2, when multiplied by its transformed pivot column, in yellow, in iteration 3, gives a scalar product 1. Also, if that fuchsia vector is scalarly multiplied by the vectors, in blue, in the iteration 3, give 0, that is, it is orthogonal to them. Therefore, the orthogonal subspace to the subspace generated by a2, is the one generated for the three blue ones, but it is also, by the three blue vectors of iteration 4, and also, by the three blue vectors of the final table, because the scalar products are all 0. In addition, the scalar product of the fuchsia vector by the yellows are always 1. Then, also those three vectors, any one of them, generates us the complementary subspace. If we do the same with the third vector, that new vector a3, the 0 0 1 1, by multiplying it by the transformed pivot vector, in yellow, it gives us scalar product 1, and by the others 0. In the next iteration, those properties of those columns remain valid until the end. The same could be said of the vector that we enter in iteration 4. Then, it's very important to see that the last table, that simply is a 4x4 matrix, contains information about orthogonal subspaces and complements of each of the vectors that we have been entering. In this final matrix, that we have repeated it 4 times, what happens is that we have used different colors, because we are interested in different orthogonal subspaces. In the first case, our interest is in the subspace orthogonal to the subspace generated by the first vector a1, that we have entered. Then, we take the 3 vectors w2, w3 and w4, for the case of this vector, which we have bold-faced in the matrix on the right. If we are interested in the subspace orthogonal to the space generated by a2, the second row of the matrix, which you have, in bold, in the second matrix that appears there, then what we have to do is to choose the vectors in blue, corresponding to the vectors that have not been used as pivot when vector a2 was entered, and the complementary is the yellow one, and analogously, with the third a3, and fourth a4 vectors. It's interesting to see that we not only get the orthogonal subspaces to each of them, but we can also calculate those corresponding to subspaces generated by any subset of these vectors, by the first and the third, the second, third and fourth, or the fourth and the second, etc. Simply, what we have to do in the final table is to eliminate the columns with which we have pivoted when we have used those vectors that generate the space, and the vectors that remain, they will generate their orthogonal subspace. Therefore, the orthogonalization algorithm, not only does it help us to get the subspace orthogonal to the subspace generated by a vector, but it serves to get the subspace orthogonal to the subspace generated by any subset of vectors, with which we give much greater interest to this algorithm. In this transparency, what I try to express is to show what happens when we use the algorithm. We start, at the beginning, with the vector a1, that you have there, and a starting matrix B super 1, we pivot, and we get a matrix B super 2, we enter another vector a2, and we pivot, and so we repeat, until we reach the end. Then, among the resulting vectors there are some that will have the letter W, and others that will have the letter V. Those that they have letter W, it means they have been used to pivot, and those that have letter V, that have not been used to pivot. Then, from this last matrix, you just have to eliminate those columns that have been used for pivoting, to obtain the generators of the orthogonal subspace of the subspace that we have chosen. Therefore, the algorithm is an algorithm very elegant, very powerful, that has some really amazing properties, like this one to keep those properties of that the scalar products, for the pivots B1, and for the no pivots B0, that really surprises anyone.